Okay, today's video is going to be shorter than usual, especially because I don't want to burden you with too many things before the exam, and because I will be planning to make a video with what are the important concepts that you should know before the exam, just a review video kind of thing. Okay, at least mention the important concepts you should know. Okay, so what did we see last time? We were looking at pseudo-random functions, pseudo-random functions, and we said we can look at the keyed functions, which are let f be a deterministic function from 0, 1 to the n cross 0, 1 to the n to 0, 1 to the n be an efficient deterministic algorithm. We define fkx by f of kx. And we said that the first input is, in that case, we are going to call that as the key. First input is called the key. Okay. And we had assumed that f is length preserving. Assume f is length preserving, i.e. f of kx is only defined if length of k is equal to length of x, which makes sense because we are taking it from 0, 1 to the n, 0, 1 to the n, and in which case absolutely the length of f of kx is equal to length of k is equal to length of x is equal to n, right? And what did we do with this? We said that choosing a uniform k in 0, 1 to the n is equivalent to choosing the function fk from 0, 1 n to 0, 1 n, and this defines a distribution on the space of functions that we can choose, i.e. for fixed length n, the algorithm f defines a distribution on function over functions in the space of all functions that we were considering, and see n. Okay, this is what we had talked about. Now we can, instead of saying that multiple things can map to the same thing, we can look at a one-to-one function. What are some of the most common one-to-one functions? Well, there are permutations. So we can look at pseudo-random permutations. pseudorandom permutations, PRPs. Okay. What is a pseudorandom permutation? Let F belong to FUNCN. F is a permutation if it's a bijection. F is a permutation if and only if it is a bijection. i.e., which is to say, this means that the inverse function exists. That inverse function exists. Okay. So let perm n be the subset of FUNCN. Okay. Be the set of permutations. Be the set of permutations. Okay. Quick question for you guys. Question. How big is perm n? So last time we calculated what do you call FUNCN, right? More or less the same idea is going to apply to calculate perm n, except now you have to make sure that all your n-bit strings are distinct, right? So you have to be slightly careful. Not only are you dealing with functions from 01 to 01, so you're not looking at like all random strings, you're actually looking at strings which are all different as n blocks. Okay, it's not too hard. Think about it. Okay. So let F be a key length preserving key be a length preserving keyed function. So let F be a length preserving keyed function. Okay. Then F is a permutation. F is called a keyed permutation. Is a keyed permutation if first Fk is a permutation for every k. Fk is a permutation for every k. Okay, and Fk inverse is efficiently computable. Where Fk inverse of Fk of x is equal to x. Okay. So efficiently computable is again going to be, you can compute it in polynomial time. For example, given a matrix, you can compute its inverse in polynomial time. The complexity becomes large very fast, but it's still computable within polynomial time. Okay. F is pseudo-random permutation. F is a pseudo-random permutation. If Fk for a uniform key k for a uniform key k belonging to 0, 1 to the n is indistinguishable from a permutation, from a uniform permutation, is indistinguishable from a uniform permutation f belonging to perm n. Okay, so we don't want to say it is indistinguishable from every other function, but we are saying that it has to be indistinguishable from a permutation, uniform permutation. Okay, that's good enough. Now, what does happen is for a large enough n, note, for a large enough n, a random permutation is actually indistinguishable from a random function, is indistinguishable from a random function. Okay, if you have a large enough n, the chance of a random permutation is more or less the same as the chance of a random function, and so you don't have, even if we are saying that it's indistinguishable from a uniform permutation, it is actually indistinguishable from a uniform function. So in practice, PRPs are also good PRFs. PRPs, which is pseudo-random permutations, are also good pseudo-random functions. Okay. Now, the idea is, okay, I have been talking about pseudo-random functions and pseudo-random permutations, but none of these are directly helping me with my algorithm, because my algorithm used a pseudo-random generator. How do I use pseudo-random functions for pseudo-random generators? Here's how we do it. PRFs versus PRGs. Okay. The pseudo-random pseudo-random function f immediately actually gives you a pseudo-random g. PRF, a PRF f immediately implies PRG G. And the method of construction is as follows. Define G of k is equal to f of k of 0, 0, dot, 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 concatenated with f of 0, 0, dot, 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 then a 1, concatenated with dot, 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 all the way up to f of 1, 1, dot, 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 1. And you get an extremely long string of, what do you call, of pseudo-random bits. Okay, so i.e. g of k is equal to fk of 0, concatenated with fk of 1, concatenated with all the way up to fk of 2 to the n. Actually, minus 1, minus 1. Okay, where the symbol denotes the n-bit encoding of I. Okay. Which also gives you that PRFs can also be viewed as a PRG with random access to exponentially long output. PRFs can be viewed as PRGs with random access to exponentially long output. Okay, why is it an exponentially long output? Because what is the length of this string? The function fk, the function fk can be viewed as a n times 2 to the n bit string, n times 2 to the n bit string, which we saw as before was fk 0, 0, 0, 0, concatenation f of fk of 1, 1, 1, 1, 1. Right? We saw that the size of these functions is, as a string, is n times 2 to the n bit. And so using a key of n bit and some function f, I can get a n times 2 to the n bit string that's exponential in n, right? So that's why these are really good. But the question is, do these really exist? Can we really find pseudo-random functions, or are we saying that great, it would be awesome if such a thing exists, but they don't really exist? Is that what happens? Do PRFs, PRPs exist? Well, they're a stronger primitive than they are stronger primitive than PRGs, right? Because we can say that if a pseudorandom function exists, then I can definitely create a pseudorandom generator from it. So pseudorandom function existing implies pseudorandom generator exists. However, you can also go the other way around, okay? However, they can be created from PRGs. So showing that a pseudorandom function exists is the same problem as showing that a pseudorandom generator exists, because you can use one to create the other. Can we show that pseudorandom generators exist? That was a debate we had some time ago, where we said we can't really say pseudorandom generators exist without some assumptions. That is, P is not equal to NP. There are some algorithms which we assume give us pseudorandom generators, but we can't prove that. right? So for all practical purposes, we assume that such functions exist and we know how to do it, but we can't really prove that these are actually pseudorandom functions. Okay. In practice, block ciphers are used. Block ciphers are used. Okay. How we use them, we are not going to get into that right now. But what are block ciphers? Block ciphers. So block ciphers are practical constructions of pseudorandom functions. Block ciphers are practical constructions of pseudorandom ciphers. Random. It's not ciphers, pseudorandom permutations. And we don't have the asymptotic length. So no asymptotics. The function f from 0, 1 to n. We don't generally define it for so one thing I didn't actually mention, I was actually hiding it because I thought it was not necessary, was that generally when you're defining functions, you don't need the functions to be having the same n. You can have these as arbitrary. You can have this as a, b, and c, some random numbers. You can define functions this way, okay? But for our normal work, we don't want them random. We want them to be length preserving, and so we assume all three of them to be n, which is why I write n. But for normal purposes, you could take these functions from any random a, b, and c, not necessarily equal, okay? So in this case, for example, these are not absolutely random. So um, generally, completely random functions, you have no restriction on n, m, and m. They can be uh, any um, any length. Okay, a, b, c can be completely independent. For block ciphers, the first one, the first one and the second one can be technically independent, which is n is actually your key length, m is your block length. You can have these two independent, but your output has to be the same length as your block length. Okay, so these have to be the same. If they're length preserving, everything will be the same, but even otherwise, for block ciphers, we always have to have n, m, and m. Okay, so the idea for these ciphers is, again, these are hard to distinguish fk from uniform f, which is a permutation, even for attackers running in exponential time. Okay, So instead of just polynomial time, we can define block ciphers so that they're hard to distinguish even for exponential time. Okay. Nowadays, the standard security that is used is AES security. We'll talk about that later. Is advanced encryption security. So we don't actually use block ciphers and things. Okay. But this is stronger than CPA security also. And there's not much reason to use anything else, but we'll get to it later. So last time we saw CPA security by creating the experiment that demonstrated whether something is CPA secure or not in the following way. Fix by A, define a randomized experiment, private key of A comma pi with which is CPA secure of n as follows. In the first step, given a key, generator generates a key of length n, sorry, not length n, given a security parameter n, the generator generates a key. So these should be just 1, 2. Okay. A1 to the n interacts with our encryption oracle, interacts with encryption oracle ENCK, and then outputs two functions m0, m1 of the same length, and outputs two functions of its choice, m0, m1 of the same length, The length has to be the same as the key generated by the generator, but that is assumed. Okay. Then we choose a random bit 0, 1 and encrypt the message MB using our encryption oracle MB. Okay. And give this to C and give C to A. Right. A can continue to interact with encryption oracle. A can continue to interact with encryption oracle. Okay. And in the final step, A has to output A outputs B prime, and we say that the experiment is succeeded. A succeeds if B is equal to B prime, and experiment evaluates to 1 in this case. And experiment evaluates to 1 in this case. Right. This was my definition of the experiment, and I said that my system is CPA secure against chosen plaintext attacks. Definition: Pi is secure against chosen plaintext attacks. Which we called CPA secure. If for all PPT attackers A, if for all probabilistic polynomial time attackers A, PPT attackers A, there is a negligible function. There is a negligible function epsilon such that the probability of the experiment succeeding a pi CPA of n is 1 is negligibly more than 1/2. This was what we called CPA secure. Now the question is, how do we create such an encryption? Okay. How should my encryption oracle work? So, CPA secure encryption. Here's how my oracle is going to work. Let f be a length preserving keyed function. Be a length preserving keyed function. Okay. Then generator 1 to the n chooses a uniform key. Chooses a uniform key, which is going to be of length n. Okay. Now, how does encryption work? Encryption k of m for message m length same as k does the following. Choose uniform r belonging to 0, 1 to the n. So this is called the random vector or vector. And the output ciphertext C is equal to R, comma, Fk R XOR sum M. Okay. Would M equal to length of K, or should it be? Just let me check. Okay, that seems correct. Since it's length preserving. Ah, yes, since it's length preserving, everything is of length n. You're correct. I'm correct. Okay. And then decryption K of what you get is C1 and C2 is output C2 XOR some Fk of C1, which is just Fk of R. Okay, and the correctness is immediate. Therefore, M is equal to R. Sorry. Equal to. Okay, the correctness is immediate because, well, what is C2? C2 is Fk of R XOR some M. I am XORing it again with Fk of C1, and C1 is just R in my ciphertext. So I'm basically XORing twice, and so correctness is immediate. Correctness is immediate. The proof that it's actually secure, however, is extremely long, right? Not extremely long, it's slightly long and slightly complicated. So I will leave that for class after the exam. I won't do it right now. I'll just state the theorem. If f is a pseudo-random function, if f is a pseudo-random function, then this scheme is CPA secure. Okay, so as long as f is a pseudo-random function, this scheme is going to be FPA secure, but otherwise we have no guarantee. Okay, I will stop this video here. I will upload another video containing the important points that we are going to cover in the chapter in the exam. Okay, and what are the things you should know. Okay, let me stop here.